Chloe, it's great to have you here for this episode. Today we're diving into something pretty fascinating, levitating micro-actuators. You know, those tiny devices that can actually float without touching anything, suspended by magnetic forces.
Yeah, Liam, it's such a cool concept. I mean, imagine a microscopic disc just hovering in place, no friction, no wear and tear. It's like science fiction, but it's real technology now.
Exactly. These levitating micro-actuators, or LMAs, are opening up new possibilities in sensors, gyroscopes, even micro-robots. The frictionless movement means higher precision and longer lifetimes.
And the way they levitate is through electromagnetic forces, right? Either static magnetic fields or inductive ones that change over time.
Right, and inductive levitation is especially promising for microsystems because it uses time-varying magnetic fields generated by micro-coils. These coils can be fabricated right on chip using standard processes, which is a big deal for integration.
That's a huge advantage. But I guess the challenge is understanding exactly how these magnetic forces work on such tiny levitating objects. Modeling that must be pretty complex.
Oh, definitely. The electromagnetic interactions, the induced currents, the forces, the stability, it's a complicated dance. Traditionally, engineers use finite element method simulations to model these systems, which are accurate but can take a lot of time and computing power.
So if you want to design or optimize a new micro-actuator, running these heavy simulations every time would slow you down a lot.
Exactly. That's where this new semi-analytical method comes in. Instead of modeling the entire complex device directly, it replaces it with what they call a filament-twin.
Filament-twin? That sounds like a simplified skeleton or blueprint of the real device.
That's a great way to put it. The filament-twin breaks down the coils and the levitating disc into simple geometric elements, mostly circular loops. Because we have well-established formulas for inductance and magnetic forces between circular loops, this approach lets you calculate key properties much faster.
So it's like trading some of the complexity for speed, but still keeping enough detail to be accurate?
Exactly. It's a sweet spot between full numerical simulations and overly simplistic models.
I read that there are two calculation schemes within this method. Can you explain those?
Sure. The first one, Scheme 1, models the induced eddy currents in the levitating disk as a finite set of circular loops. It's simpler and faster but less detailed.
And Scheme 2?
Scheme 2 meshes the disk into many small circular elements, capturing the current distribution more precisely. It's more accurate, but requires more computation time.
So depending on whether you want a quick estimate or a detailed analysis, you pick the scheme that fits.
Exactly. Both schemes use the same underlying physics, but differ in how finely they represent the eddy currents.
I'm curious about how the method actually works. I mean, the disk is levitating and moving in space, right? How do they model that?
Good question. The levitating disk is treated as a rigid body with 6 degrees of freedom, 3 translations, and 3 rotations. The coils carry alternating currents at high frequencies, often above 1 megahertz, creating time-varying magnetic fields.
Those fields induce eddy currents in the conducting disk, which then interact with the coil currents to produce the levitation force.
Exactly. The method calculates the magnetic energy stored in the system and then derives forces and stiffness by differentiating that energy. It uses Lagrange-Maxwell equations from analytical mechanics to describe the coupled electromechanical dynamics.
That sounds pretty heavy mathematically.
It is, but here's the clever part. Because the electrical processes happen much faster than the mechanical ones, the model assumes the mechanical behavior is quasi-static relative to the AC currents. That simplifies the calculations a lot.
So they linearize the model around the equilibrium levitation position to analyze stability and dynamic response.
Exactly. That way, they can predict not just the levitation height, but also how stable the levitation is and how the system responds to disturbances.
That's impressive. But theory is one thing. How well does this method hold up against real-world devices?
They actually validated it on several real prototypes, both planar and 3D microcoil designs.
Like Sherwood's prototype?
Yes, that's a classic. It uses planar microcoils to levitate a tiny aluminum disc about 250 micrometers in radius. The method accurately predicted levitation height and magnetic stiffness, with both calculation schemes matching experimental data and 50 MEM simulations closely.
And Zhang's prototype?
That one's more complex, with stabilization, levitation, and rotation coils. The method modeled levitation height and lateral stiffness, showing how lateral stiffness changes with levitation height. It also predicted lateral force versus displacement, helping identify the stability zone for the levitating disk.
So it's not just about levitating, but also about how the disk behaves when pushed or displaced.
Exactly. Then there's Wall-Raby's prototype, a 3D micro-coil design fabricated on hollow posts. The method matched experimental levitation heights and stiffness values, and even mimicked direct force measurements in vertical and lateral directions.
Capturing nonlinear stiffness behavior and stability limits too?
Yes, which is quite remarkable. And finally, Poletkin's prototype, another 3D design with different coil parameters, also showed good agreement between the model and measurements.
That really shows the method's practical utility.
Absolutely. And beyond analysis, the method is great for optimization.
Like finding the optimal radius of the levitation coil to maximize levitation force?
Exactly. There's a Goldilocks zone for coil radius. Too small or too large reduces magnetic flux and force. The method found optimal coil sizes close to those predicted by FEM, but with much less computation.
That's a big deal for design efficiency.
Another example is adjusting the vertical position or offset of the stabilization coil to maximize lateral stiffness.
Which improves the maximum stable rotation speed of the device, right?
Yes. The method showed that raising the stabilization coil by about 100 micrometers can double lateral stiffness, enhancing performance significantly.
So these optimizations can reduce power consumption or increase payload capacity.
Exactly. It's a powerful tool for engineers.
When you think about it, this method really balances accuracy and computational efficiency, enabling rapid design iterations.
Right, and it supports the development of advanced microsystems with multifunctionality, multi-stability, and improved dynamic performance.
Plus, it can be extended to other magnetic devices, including those using permanent magnets or hybrid force fields.
So it's not just limited to inductive levitation, but has broader applications.
It's exciting to see how foundational research like this pushes forward micro-scale actuation and sensing technologies.
Definitely. From MEMS to gyroscopes to micro-robots, this kind of modeling is key.
To wrap up, I'd say the main takeaway is that by cleverly simplifying complex electromagnetic systems into manageable filament models, we can accurately predict and optimize the behavior of levitating micro-actuators.
Yeah, it's a beautiful blend of physics, engineering, and math that makes these tiny, precise devices possible.
And it's a reminder of how much goes on behind the scenes in the tech we often take for granted.
Absolutely. Well, thanks for the great chat, Chloe.
Thank you, Liam. Always a pleasure.